Hi all, this is Adam Hagazi and I'm with Ahmed Wael and we're going to present to you the anime aging. So this is table of contents. First, we're going to start with the problem statement. Our problem is that we want to create a model that ages and de-ages anime characters from seniors to teen and vice versa. So as you can see, this is expected input and output. As an input, we can have a teen anime character that we can age to a senior one and vice versa. So the model architecture that we chose was the cycle GAN, as it can map an image from a domain A, as you can see here, like the horses, and it can map it to domain B, to the zebras. We can have here discriminator, which compares the generated image from domain A to the images from domain B. And then it can map it back again, reconstruct it back again to its original domain, and it calculates the consistency loss to make sure that the reconstructed image has similar features to the original one. So the base cyclic GAN model that we chose was the implementing cyclic GAN for age conversion by Matcha, which had the privilege of unpaired datasets, working with unpaired datasets, meaning that we do not have to have the same image for the same person once as a teen and once as aged. And it also worked on human aging, which is a similar domain to, which is a close from the domain that we're working with, which is anime. So this is the architecture of the base model for the generator. This is a generator network for each generator. As you can see, we've discussed before that we have two generators, and then the discriminator. This is also the architecture for each discriminator, each of both discriminators. So our solution was our main proposal here is the domain transfer, since no one worked on this specific domain of anime characters before. So we had to obtain our dataset by so we had to obtain the dataset as we do not have dataset for ourselves, and we had to do some data cleaning and augmentation and modification, hyperparameter tuning, which we'll discuss next. First, we started by scraping the data, does not have the dataset. Then we had to crop it to the faces of the anime itself. And then we had to do a lot of data augmentation because data set was not sufficient for the GAN model. And then we had to work with the base model and do some variations on it, and then do some quantitative evaluation. We'll discuss each that. So first, by the data, as I mentioned before, we scraped the data and then we cropped it from full body images to faces only. And we also had augmented the data and increased the senior data set by 200%. Using horizontal flipping and brightness and contrast modifications.
Now, continuing on from what Adam was mentioning and moving on to the model, in bold, these are the main hyperparameters that we modified in our throughout our project. Those included things like the image size, some activation functions, some losses, other things that had to do with batch size, and some base filter size, of which other filter sizes was a multiple, and the discriminator tunability, or essentially its freezing in the combined GAN. The values highlighted in bold are the ones that we decided to stick with, and you will see that the cycle consistency loss we decided to stick with too, and we will mention that right ahead. Another thing that we introduced to the model that was not existing in the base model by Matcha is quantitative evaluation, whereby we use the Frecht inception distance to assess the quality of the different variations of the model. This is a metric that was introduced by Husel and others in 2017. It's a very popular metric for GAN evaluation. It uses the Inception 2015 version 3 pre-trained model, and it measures the similarity between feature vectors of two groups of images. Now let us move on to results. These are some of the variations that we mentioned. As you can see, we only highlighted specific variations, not everything, namely the image size, losses, activation functions, and the right two columns are the FIDs that we will find for A, which is the teen domain, and B, which is the senior domain. Feel free to look at the results in more detail. Here are the results represented as a bar chart, and we highlighted in orange the two most successful models that we had, which were Model A and Model C, which you can see both had ReLU as their middle activation functions, TANH as their output activation functions, both for the generator. However, they only varied from one another in the cyclic loss and the identity loss, and they also had the same image size. Now let us move on to the demonstration. The side that was not showing was the output. We'll make sure to include that in the video. This is our demo. As you can see, the cells that we have already run before, we load the model with the weights that we want, and now we run this function, which generates a senior from a teen, and this function, which generates a teen from a senior. Thank you. As you can see, the cells that we have. Now, for the conclusion and the future work, some of these conclusions are like our personal achievements, and other are more project-based. Thankfully, we were able to study GANs in depth in this project, as this was something that we didn't really have the opportunity to do in the course. And GANs in general, as well as the recent advancements in specifics, such as, for example, the validity layer in the discriminator that had to do with patch GAN. We also have a more like objective conclusion, which is that GAN evaluation should not be completely dependent on quantitative metrics, such as FID, because while they are more efficient in terms of time, they are not always the most reliable. And that was seen because Model A and Model C had some variation in FID. However, Model C was almost visually the same success as Model A. And another thing is that pioneership is very difficult, and that we have exerted a lot of effort and spent time on a lot of extra and secondary objectives that don't have to do with training the model, because we are the first people to explore this domain. For the future work, in general, we believe that our model is the first step for anime character aging and de-aging, and this is an achievement in and of itself. Our dataset is another achievement, because anyone who needs datasets for anime-related models can use that dataset and the scraper to generate even more data. Implementation of FID is useful for cycle GAN models in general, because the model that we had did not have FID. We introduced that. Other more technical things that can be done, maybe future researchers can have image size thresholds, as very small images we suspect that they are the cause for some of the bad results that we are having. And we also looking into varying the cyclic consistency even more, because a lot of the images were reconstructed very well, however, showed minimal aging and de-aging in the in the important output. So maybe try to put less focus on the cyclic consistency and more focus on the generation and discrimination. I will now just simply show you the slide that was not showing. And this is a sample of the output of Model A and Model C. The two models had identical hyperparameters except for the cyclic loss and the identity loss. Thank you.